Hello there, and welcome to this mathematics class presented to you by O3 Schools JAMB app. Now, okay, you must know your O3 Schools JAMB app is an application which can install on both Android phones and your laptops, coming soon for iPhones definitely, which helps you create a platform or a software where you can actually practice for your JAMB. So first of all, it has a normal past questions, and it also has where you can set it into mock exam mode. In mock exam mode, it shows you the software looking pretty much as the software you would see on the day of your jam. So this software you can try practice and get used to how this system operates. So if you practice with this on a laptop, for example, you'll be very comfortable when using the computer system you'll be given on the day of your jam. The School app is very fun and very versatile. And by versatile, I mean you can actually adjust the settings to suit you as you prepare for these examinations. For example, you could choose the number of questions. You could also alter the duration, the time you are using. You could even choose the particular topics you want to answer or the ones you want to remove, and many other factors like that. And also, even when you are done, within the correction you would see, you would also see a breakdown of how much time you spent on each, the particular topics the questions were brought out of, and which topics you did well in. If four questions came from a topic, you would see that you scored 2/4 in this topic, but maybe 1/5 in this other one, telling you need to work hard on this and to help you assess your strengths, your weaknesses, even and including the time you use. The three schools app is actually very useful for any student who want to get a very good score in their JAMB. Now, upon the installation of this app, you realize that you are quite limited with the features you can use originally, and that's because the app is not activated. So, to enjoy full functionality, you must buy your activation key, and the activation key costs 2,500 naira. This is the cost of the activation key. So, without the activation key, your app's functions are quite limited. But once you get your activation key, the app becomes very easy to use. And within your app right there, you see the space to buy activation key. And when you get there, you see the different choices, different ways with which you can buy the activation key. Either paying through Google Play, paying online, which means you'll be paying through PayStack using your debit card, or you could simply do a bank transfer. Whichever method you use, it doesn't matter, but your app is guaranteed to be activated. To get your 3 Schools Jam app, and once you have it, come with me on this journey as we look at a very important topic in mathematics, and that is differentiation. Differentiation. This is one of the most important topics in mathematics, and one you are guaranteed to see in your JAM. There's no avoiding it. You must see a differentiation question or more. And what's differentiation? Well, differentiation simply measures the change in one variable when there's a change in another variable. Quite simply, if y was equal to 2x, define the derivative when you are being asked to differentiate y. Simply means find what happens when a small change in x. When there's a small change in x, find what will happen to y. What kind of change will there be in y? And in this topic, our differentiation or our derivative is usually presented in the form, let's say I have y as an expression, and this expression is a function of x. By function of x, we mean to be maybe x squared plus 5. It just means that in that particular expression, x is a variable. In that case, find the derivative of y with respect to x. Now, so this dy x is quite common. You must have seen it before. Now, when you are dealing with dy dx, it means you are differentiating y with respect to x, meaning we have to find what happens when there is a small change in x. Now, please keep in mind, there could be other variables in the question. Say, I was having y equals to 4k squared. If I'm then asked to find in my question dy dx, this expression doesn't have x at all. Correspondingly, if there's a change in x, does that affect k? No. So in that case, my derivative will be 0, as we'll see very soon. But On the other hand, if I was asked to find when there's a small change in k, that becomes dy dk. So I know a lot of us are very, very used to dy is x, but please note that dy dx is not the only way you could differentiate. You could find basically d of any letter to any other letter. So dk dt simply means, if you're having a question, dk dt, that means find the derivative of k with respect to t. So it doesn't really matter what the letters are. This first letter always represents your function, while the second letter, the denominator, represents your variable you are finally changing. So that's how differentiation works. And please note that this could also be rewritten as simply y prime. This is the same thing as finding the derivative. And could also be written as f prime of x, because y was equal to f of x. So any of these three you see, they all mean the same thing. In fact, in some cases, let's say y equals to the expression 4x squared plus 3. At times, instead of telling you to find dy dx, they'll speak to you, find d dx, this is x, of 4x squared plus 3. This is the same. This means find the derivative of everything you have in this bracket with respect to x. So however it is written, the method of solving doesn't change. And now, how then do we actually do this solving? Well, most commonly, differentiations can be done using something called the first principle. It is a very long step, depending on the question, which we truly do not need to cover in this class, because as far as JAMB is concerned, you can simply use what is known as a standard table of derivatives. So the point I'm trying to make here is there is a long method of solving it. However, that method is quite long and cumbersome that for most exam purposes, especially in OBJ, we use a standard table of derivatives in which they tell us when you see something like this, then you must differentiate in a certain manner. So it is that standard table of derivatives we are going to be taking a look at. So want to look at the table of derivatives. So on this side of the table will be my y, which is f of x. And then on the other side of the table would be my dy dx, or f prime of x, or y prime, whatever symbol gets used in that particular instance. So first of all, what if I simply have a constant a? A here represents any number at all, anything at all. So as we have a constant a, then my derivative is always 0. Is that easy? If you're asked to find the derivative of 5 with respect to x, there's no x here. That makes this a constant. My answer is 0. If you have to find the derivative of 2b with respect to x, there still is no x here. That makes my answer 0. So as long as the variable I want to differentiate does not exist in my expression, my derivative is always 0. That's the first thing we must know. And secondly, I was asked to find the derivative of simply x. My answer is 1. So the derivative of just x always gives you 1. Next up, what if it was ax raised to power n, where a and n are constants? This could be written simply as, let's say, 5x to power 2. This is an example. This is my x. This 5 represents my a there, and this 2, the n right there. And as a result, if I find the derivative of this, what I get would be the number behind times the power, that's a times n. Then I write my x, then I subtract 1 from the power. It is that simple. If I also try that here, that will give me 5 times 2 is 10. And if y equals this, then dy dx must be 5 times 2, 10. Then I write my x. then 2 minus 1. And as you are aware, 2 minus 1 is 1. And I do not really have to put the 1 there. So that is my answer. So you see, the table of standard derivatives tells you what to do whenever you come across a question. So I have that. Next up, let's look at derivative of sine x. If I was asked to differentiate sine x, the answer is simple. It will always be cos x. While on the other hand, if you're being asked to differentiate cos x, then the answer becomes negative sine x. Then if you're also asked to differentiate tan x, the derivative is sec squared x. Now, keep in mind, please, like I said previously, everything on this table has to be memorized. You have to know each and every one of them so you can actually apply them in your solvings. These are things you have to cram quite simply. So we have this. Then what if there's a number with them? If I was having sine ax, sort of like saying sine 5x, what happens is quite simple. We simply differentiate what we have right here. And as you are aware, if I'm having ax, that looks something like this. And its power is 1. A times 1 is a. Then power subtracts 1. 1 minus 1 is 0. And n to the power 0 is 1. Implying just a comes out, which means a comes out here. And as we learned here, this sign turns into cos. And then we write back what was here before, ax. In the same way, if it was cos ax, now a will also come out, but then there's a negative sign, minus a sine ax. If it was tan ax, a also comes out, a sec squared ax. Okay, what if it was log to base e of x, the natural logarithm of x, which can also be written as saying in x? You can see that symbol in the calculator. This and this have the same meaning. In that case, you simply get 1 over x. So derivatives are quite simple. Simply, first of all, memorize your standard derivatives. Once you know the standard derivatives, we'll learn a couple more things and we are good to go. So let's see what else is there for you to know before you can actually start your solving. Well, if you notice, all these standard derivatives were standalone variables. And what do I mean? These were all variables which were staying on their own. There were no two different types of variables together. For example, imagine a particular question we're having sin x times cos x. This one has its own derivative. This one has its own derivative. Do I just differentiate both and multiply together? Well, no. And we're about to learn what we ought to do in such situations. So, there are several rules we obey, and the first one is known as the chain rule. The chain rule. And this rule governs plus and minus. So if I have several variables all adding or subtracting to each other, say y equals to u of x plus v of x. This could even be plus or minus, it doesn't matter. The rule stays the same. In this situation, dy dx becomes, differentiate the first one, du dx, then put the symbol the way it came, plus or minus, and then differentiate the second variable. That means if I have any variables adding or subtracting, I simply differentiate them one by one. I'll give my sign exactly the way it came in my question. So that's chain rule. Up next, we have product rule. And as the name implies, product rule governs multiplication. What if they are multiplying? So say y equals to u of x times v of x. How do I get dy dx? Well, this one is a little bit tricky. The simple method is you pick one of the variables between u and v. You can pick either one. Say I take u first. I'm going to then differentiate the other variable, dv dx. So I picked one without changing it whatsoever, multiplied by the derivative of the other one. Then always put a plus in the center. Then I'm now going to pick the one I did not pick before. I picked u before, so now I'm going to pick v and then differentiate the other one. So when I picked u, I differentiated v. When I pick v, I'm going to differentiate u. And this is how you find the derivatives for product rule. That means if two of them are multiplying each other, this is your simple method. Pick one, differentiate the other, plus pick the other, differentiate the first. Okay, next up we have quotient rule. Now, again, as you should know, quotient rule works for division. So, if we have the variables dividing each other, u of x divided by v of x. I'm symbolizing that these are functions of x, so I will know where I find dy dx. That then means that in this case, dy dx is, now, question 2 is actually one of the trickiest ones, but just pay attention. Take your denominator first, hold your denominator, then differentiate your numerator. That will be du dx minus, hold your numerator now, and differentiate the denominator, dv dx, all over the square of denominator. It is that simple. So please note, in product rule, you can mix them up. It doesn't matter what you do first, because an addition sign in the middle, and the addition, as we know, is commutative. 2 plus 3 is 5, 3 plus 2 is 5. It doesn't matter which comes first. However, here we are subtracting, and as we know, 3 minus 2 and 2 minus 3 are not the same thing. That means I have to be careful. It's always hold the denominator and then differentiate the numerator, minus hold the numerator, differentiate the denominator, all divided by the square of the denominator. Is that okay? Good. Now, there's a fourth one we're going to look at right now, but this doesn't cover any normal operation. This method applies when you seem to have a variable that is, how to put it now, a little bit tricky to deal with. Say, for example, I have y equals to sine x raised to power 3, sine x cubed. This means sine x times sine x times sine x. Now, if I try to solve this in the usual way, I'm going to use product rule, but you notice that will be a bit tricky because there are now 3 products and it's stressful. Can I always multiply? What if there are 4 products? What if there are 5? I'm not going to multiply all 5 together. But there's a simple trick we use. In this case, we're going to remove this variable and replace it with a simple letter. Let's say I replace that with u. So now I'm simply having u cubed, which, as you are aware, is a very, very simple thing to differentiate. So what do? Once I differentiate this, I'm also going to differentiate this, then I'll do a little multiplication. Quite simply, dy dx becomes dy du times du dx. Because as you are aware, du will cancel out du, leaving me with dy dx. So if ever you have an expression like this, you can actually substitute. Let's say y equals to u is power n, or we may say when y is a function of u and u is a function of x, that's when we apply this. If we have y expressed in terms of u and we can express u in terms of x, if what we're trying to get now is dy dx and not dy du, now simply find dy du times du dx. So typically, the u doesn't come in the equation. We create the u ourselves. So if I've asked you something like this, say for example, y equals to 2x minus 3 or 5 as I wrote there, or raised to power 5. In that case, rather than expanding this bracket to get it in linear form, which will be stressful, or send out to use product through when there are 5 things multiplying, I simply say, let's turn everything in here into u. Y equals u raised to power 5. And as such, I can find dy du. Dy du will be, there's a 1 here. 1 times 5 is 5. U. 5 minus 1 is 4. Then also, u equals to 2x minus 5. And I can find the u dx. Differentiate 2x, you get 2. Differentiate 5, you get 0. So I'm left with 2. And as such, my answer will be dy du, which is 5u raised to power 4, times du dx, which is 2. So I can substitute u back for its original value. That will be 5 times 2 is 10. Then 2x minus 5 all raised to power 5 minus 1, which is 4. So I hope you get this idea. We use this when we're having a funny variable like that. So these are the 4 basic methods we use to differentiate. Now please note that there are several other methods which are not set by JAMB, which you can also read up for fun if you want. They are not covered in JAMB syllabus, but if you so desire that you just feel like learning some of these other ways of differentiating, there's nothing stopping you from learning them. And you should also know that in fact, when you learn some of those concepts, some of these previous ones you have learned before actually begin to seem actually a bit easier because you begin to understand them more. And also you must solve many questions to this topic. So get your 3 schools JAMB app, get your mathematics textbook, and just solve as many questions as you can. Practice makes perfect, especially when it comes to differentiation. The more you solve, the more those standard derivatives will stay in your head. And you can actually be able to use them to solve questions. So before I try move on and I try start solving, a couple more things you need to know. Now, we already said from y we can get dy dx. What if in a question we do not want to stop here? What if we want to differentiate this dy dx to see what happens next? Because for example, if y equals to 10x cubed, using the method with length, 3 times 10, this is dy dx, will be 3 times 10 is 30, then x, 3 minus 1 is 2. What if somebody wants to find the derivative of this 30x squared? That means he wants to differentiate what we've already differentiated before. Well, in that case, it is symbolized as d square x, d square y dx squared. So if you want to get a derivative after you already have an initial derivative, the next one is d square y dx squared. And after that, we also get d cube y dx cube. And if you want, you can also even get d raised to power 4y dx to the power 4. There's no real limit. You can keep on differentiating. You can differentiate the answer with differentiation and then differentiate all over again. It is entirely up to you. And the last thing we are looking at before I try to solve is definite derivatives. What if they want to get these derivatives in terms of whole numbers, actual numbers, not just letters? They may then ask you find dy dx when x equals to, if they like, 4 or something. Well, this is not particularly special. That simply means that after you are done solving, you have to put 4 to replace the variable x. So in symbolism, it is written as dy dx, then draw a line here, x equals 4. That means after you finish differentiating y, you have to replace x with 4. If I try it in this case, I know that dy dx is 30x squared. This x is 4, that gives me 30. X becomes 4, and that is squared. 4 squared is 16. That is going to give you 480. So definite derivatives are simply gotten by replacing your variable with that constant or number that they actually want. And these are the basic concepts you need to understand for you to start differentiating. And what this simply means is that it's time for us to open our O3 Schools JAMB app and actually solve questions. We've covered a lot of theory, so we're going to solve a reasonable number of examples to actually explain these concepts we've been looking at. So, I'm just open my own O3 Schools JAMB app right here, and let us see what we can start with. Okay. My first question is from the year 2015, and this is question number 13. 2015, question 13. And this one says, if y equals to 3 sine minus 4x. If y equals to 3 sine minus 4x, I'm to find dy dx. It's actually very, very simple. Now, number one, I can see that this 3 multiplying is a constant. It's not a variable. That means I'm not going to apply product rule. All I have to differentiate is sine 4x or sine minus 4x. And whatever I get will have to be multiplied by 3. So how do I do that? Well, y equals to 3. Then you check your table of standard derivatives. This sine minus 4x should remind you of sine ax. And in your standard derivatives, we know that this a would come out, and now we have cos, then I write ax back, which means that in this case, my minus 4 will come out. My sine turns into cos, then I write my minus 4x one more time. So this is dy dx. And then, last but not least, 3 times minus 4 is minus 12 cos minus 4x. Which, opening my question back and checking my options. So I think I closed my question previously. Yes, okay. Checking my options, that is option A. So you see, differentiating is very, very easy. This is a basic question in differentiation. So I hope this is understood. Just know your standard derivative and you will know how to start your solving and how to finish it. Okay, my next one is actually to find derivative of, this is, by the way, this is 1997 question 33. This one to says d dx of cos 3x squared minus 2x equals to what? We want to differentiate, and so I can write it simply by saying y equals to cos 3x squared minus 2x. Well, how do we solve this? Well, it's really quite simple. Remember, we said if you are differentiating something, the cos of something, you have to differentiate what's inside here, right? Or if this looks confusing, we can replace with a letter. Any method works. Let's just show how we replace. If I replace this with a letter, I'm going to have y equals to cos u. Replacing everything in this bracket with u. And as a result, I know that dy dx becomes, what happened? I can't find dy dx now, can I? Because I say dy dx. Is there x in my equation again? No. Therefore, what I'm trying to find now is dy du, because my variable is now u. And what happens? So we'll differentiate cos. No, the derivative of cos is always minus sine u. So dy du is minus sine u. But can I stop here? No. I also have to remember that u, like we assumed, was equal to 3x squared minus 2x. Let's then find the derivative of u with respect to x. Du dx would be, they are subtracting, that means it's chain rule. And in chain rule, I simply differentiate each element individually. So let's see what happens here. 3 times 2 is 6. X appears, and 2 subtracts 1. Minus, there's a 1 here, obviously, invisible 1. 2 times 1 is 2. X remains, then 1 minus 1. So obviously, that must give me, this is still du dx that I'm dealing with. 2 minus 1 is 1. I don't have to write 1 in symbol. So 6x minus 1 minus 1 here is 0. X to power 0 must be 1. And 2 times 1 is 2. So now I know du dx and I know dy du. And remember we said if we ever substitute, dy dx must be dy du times du dx. And do I have both of these already? Yes. Dy du is minus sine u, and du dx is 6x minus 2, which means I'm having minus times this, minus open bracket 6x minus 2, then sine, and we know that u equals this. So rather than writing u again, I'm going to bring back my u in its original form, which is 3x squared minus 2x. And then let's check our options to see if it was expressed in this form. To check my options, well, yes, quite clearly, this is my option D. The reason why we checked was because they could have decided to open this bracket and say minus times this and minus times this. But because in my options, the bracket was left like that, I stop here. Or you may be like, this is quite long. There's a shorter way to solve this. If I decided not to substitute, I'll still go into my bracket and say, if y equals to cos 3x squared minus 2x, then for my standard derivatives, simply differentiate what's in the bracket. Differentiate 3x squared would be 3 times 2, 6, x, then power subtract 2 minus 1 is 1. No need to write it. Minus, differentiate 2x. Differentiating any number with x is just that number. So 2 appears. This will then multiply. When you differentiate cos turns into minus sine. So minus sine, then you write back your function. 3x squared minus 2x. And if I simply transfer this minus to the front of this, that becomes minus, open bracket, 6x minus 2 sine 3x squared minus 2x, which as you can see is the same as this. So any method you apply, as long as it is correct for that particular scenario, you are guaranteed to get your answer. See, so that is that for that. Let's move on and try a couple more. Okay, this time I'm going all the way to the year 1997. That's why I'm saying I'm going all the way. It's the same year we just solved. But now I'm going to question number 32. This one is asking me to differentiate, basically write it in form, y equals to 6x cubed minus 5x squared plus 1 over 3x squared. To differentiate 6x cubed minus 5x squared plus 1 over 3x squared. And a lot of us look at this and be like, okay, they are dividing, so I should apply quotient rule. That would be correct, but please note, quotient rule, as you can see from the formula, is a little bit long and cumbersome. So if there's a way to avoid it, we like to avoid it. So check ourselves, can we possibly avoid it? And the answer is a clear yes. How so? Well, if any two numbers are being divided by the same denominator, it means I can actually separate them. For example, 2 plus 1 over 3 is the same thing as saying 2 over 3 plus 1 over 3. They both share the denominator. So this guy gets it, this guy gets it. That means in this case, I could have 6x cubed over 3x squared minus 5x squared over 3x squared plus 1 over 3x squared. And so what can happen here? 3 here is 1, 3 into 6 is 2. And x cubed over x squared is x minus, over here, x squared cancels x squared. 5 over 3 remains 5 over 3. Oh, I forgot this 2 right here, so here should be 2x. Then last but not least, from the laws of indices, this x can simply come upwards and the power becomes negative. So that is x to the power minus 2. That means this is now my equation. And in this form, they are simply adding and subtracting. So I don't have to use quotient rule. I can just use chain rule, which means I'll differentiate each of them individually. And as such, I know that dy dx must be differentiating 2x. Again, as we know, differentiating any constant that has just x in the front means the x goes away, and I'm left with the constant 2. I want to check it out is because 2 times 1, 2, x to the power 1 minus 1, and 1 minus 1 is 0. So x to the power 0 is 1. This minus, differentiate 5 over 3. Is there any variable here at all? No, there's no letter here at all. So this is a constant. As we know, when we differentiate constants, we get 0. So everything there is gone. Plus, in this case, don't forget, this is the same thing as saying 1 over 3 x to the power minus 2. It will be very, very convenient to think about it in our solving in this way. Let's do it this way and just transfer our answer back there. What do I mean? If I'm differentiating this, minus 2 times 1 is minus 2 over 3. Now I'll be having x raised to the power minus 2. And I subtract 1 from this, minus 1. And I know that that would give me minus 2 over 3 x raised to the power minus 2 minus 1 is minus 3. Okay, so the y dx will be 2 minus 0 is 2, plus times minus is minus 2x to the power minus 3 over 3. We are done, right? So let's check our options and see which option agrees with us. Then if you notice in your options, rather than having x to the power minus 3, all the options are having their x at the denominator, which means the same law of indices that let us bring this x to the power 2 upwards will become negative. Let us take this one that was negative downwards. And then that once I do that, negative power vanishes from the index. So I'm left with x raised to the power 3. And we can see very, very clearly that this is option C. You see, one more thing you should learn is not to panic when you don't see your option immediately. When you don't see your answer immediately amongst the options. This is why just a simple change or factorization or cancelling out that you need to do to get your answer looking exactly like the one in the options. So, well, this is done. It's time for us to proceed. Okay. Our fourth question comes from the year 2002. And this is question number 19. This one is very, very easy. It simply tells us if y equals x squared minus 1 over x, find dy dx. Now the only problem with this is that the x is at the denominator, but that doesn't mean it has to stay there. As we saw from number 3, if we have a denominator, this is power 1, it can simply come up becoming x raised to power minus 1. And then I can apply my dy dx because they are subtracting, that's chain rule. There's a 1 here, obviously, there's a 1 here. 2 times 1 is 2x raised to power 2 minus 1. Y over here will be 1 times minus 1 is minus 1, x raised to power minus 1, then also minus 1. This gives me 2x. 2 minus 1 is 1, and there's no real reason to write it. Then over here, minus times minus plus 1, x raised to power minus 1 is minus 2. But obviously, all my answers have their x at the denominator. So I do likewise. This becomes 2x plus 1. Taking this x because it's negative, I'm taking it back down over x raised to power of 2. And that, remember, I'm having plus now, no longer minus. So that is option A. So I hope you get the idea right now. Calculus differentiation is very, very simple. And if you did not know, differentiation is simply half of the family of calculus. Calculus is divided into differentiation and integration. So for now, we are looking at differentiation. Okay, so for my next question, this one is from the year 2001, and this is question 38. 2001, question 38, and it says, if y equals to x sine x, and to find dy dx when x equals pi over 2. So let's see, y is equal to x sine x. Now obviously, these are two different things multiplying each other, two different variables. One is x and the other is sine x. So let's separate them. Let's say u equals to x and v equals to sine x. As I'm multiplying, I now have to use product rule. And for product rule, I don't just need only u and v. I also need to know du dx and dv dx. What is du dx? Differentiate x, you get 1, as you have on your standard table. And differentiate sine x, you get cos x, also from your table of standard derivatives. And therefore, what's the formula for product rule? It becomes pick any one. Let's say I'm picking u first of all. So u stays the way it was, x, multiplied by dv dx, which we've gotten as cos x, plus I pick my next variable, which was v sine x, multiplied by du dx, which was 1. And as a result, x times cos x is x cos x. Sine x times 1 remains sine x. And when I check my options, this is not there. Why is that? Because we're not really done. We forgot this other part. When x equals pi over 2. That means I'm going to replace x anywhere I see it with pi over 2. So let's see, how do we do that? Dy dx at x equals pi over 2 becomes, this first x turns into pi over 2 times cos x, which is also going to be cos pi over 2 plus sine x, which will also become pi over 2. Now please note, in this case, the pi is being given to us in radians. And pi in radian, you should know from trigonometry, pi in radian equals to 180 degrees. So in reality, what I'm having is pi over 2 cos 180 degrees over 2 plus sine of 180 degrees over 2. That gives me pi over 2 cos 90 plus sine 90, because 180 over 2 is 90. Now, from trigonometry, you must know already that cos of 90 is 0 and sine of 90 is 1. 0 times anything is 0 plus 1, which is finally 1. And when I check my options, that is option C. So this is something you must have known, or you should know if you did not before. If you are being asked to substitute pi into the equation, pi represents 180. But funny enough, please note, pi represents 180 degrees when it is inside the cos or inside the sine. But outside it, it is still your normal pi. But within, when it's now working as an angle, sine, cos, or tan, then it represents 90 degrees. Sorry, 180 degrees. All right. I hope this is noted. This was both an example of product rule and also of finding definite derivatives. Okay. So, time to search for next question. This one is from the year 2002. Question number 16. 2002, question 16. And this is our sixth question. And this one simply says, find the derivative of y equals sine squared 5x with respect to x. Now, as you are aware, sine squared 5x can be written as sine 5x times sine 5x, which means that again, I am dealing with product rule. And how does product rule work? Well, quite simply, u equals to sine 5x and v equals to sine 5x. Well, du dx must then be differentiate sine 5x. The 5 comes out, sine turns into cos, so 5 cos 5x, and dv dx is the same as du dx because they are the same. That gives me 5 cos 5x. So now, applying the formula properly, I pick one, u, which is sine 5x, and u must multiply dv dx, which is 5 cos 5x, plus, next, I pick v, which is sine 5x, and that also multiplies du dx, which is 5 cos 5x. Opening both brackets, this gives me 5 sine 5x cos 5x, because this 5 just moved to the front. Same thing happens here. 5 sine 5x cos 5x. And we know that 5 of anything plus 5 of that same thing equals 10 of itself. So 10 sine 5x cos 5x. When I check my options, this is option D. So you see how we get it. This is simply how our question works. It's a good example of product rule in action. Okay, so let's see what else we have. Okay, let's go to the year 1998, and this time let's tackle question 28. The year is 98. The question is number 28. This one says we are to differentiate x over cos x with respect to x. Another fundamentally simple one, so as you get the logic and keep it in mind. Why is that? Because this is going to be quotient rule. I have one variable at the numerator, x, and it is dividing another variable at the denominator, which is cos x. Now, if you remember, for product, or rather for quotient rule, there's a formula. But for that formula, I need to know not just u and v. I also need to know du dx, which will be differentiating x 1, and dv dx, which will be differentiating cos x, which is minus sine x. So, how does it start? Well, the y dx, as you are aware from the formula, and if you've forgotten, let's just write it again. This is v du dx minus u dv dx all over v squared. What is v? V is cos x times du dx, which is 1, minus u, which is x, times dv is x, which is minus sine x, all over v squared. And v is cos x, which is cos x all squared. Let's finish it up this way. Cos x times 1 is cos x, minus times minus is plus, that is x sine x all over, and as you are aware, cos x all squared can also be written as cos squared x. Now, normally we would say we are done. But when you check your options, this is definitely not there. That means you have to do a further bit of manipulation. How do you know how to start manipulation? Simply look at your question. In this my question right now, none of them have denominator. And the only way for me to remove my denominator is to separate them. Meaning I'll be having cos x over cos squared x plus x sine x over cos squared x. So, as you are aware, this cos x over cos squared is the same thing as saying 2 over 2 squared. I know 2 squared is 2 times 2, so 1 cancels 1, which means my cos x here gets rid of the squared, and I'm left with 1 over cos x plus, then over here is x sine x over cos squared x. If I rewrite that over here, that's x sine x over cos x times cos x. Is there a simpler way to express that? Yes, because from trigonometry, this is why trigonometry is very important. And remember that sine x over cos x can be replaced. So this will be x, let me write them separately. Sine x over cos x. Then I'm still going to be having 1 over cos x this way. Let's recall something you should know already, that sine x over cos x equals tan x. That's knowledge that we should know from trigonometry. And also that 1 over cos x can be written as sec s. Therefore, how do I even know I should do this? Because if I check my options, I can see sec s appearing in places. So I can bring out sec x here. 1 over cos, as we've written, becomes sec x plus x. Sine over cos becomes tan x. And 1 over cos is also sec x. Now, when I check my options, I realize that yes, this is option D. All they did was that they rearranged it in their case, because addition is commutative. So they wrote theirs in this form: x tan x sec x is tan plus sec x, the same thing as our answer. So this is how you work with product rule. When they are dividing, this is a very, very simple step which will be required to carry out. And that is that for this particular question. Okay, let's move on. This time, let's see 1995, question number 29. We have been asked straightforward in this case to find the derivative of cosec s. I can say y equals cosec x. Now some of you be like, okay, how am I supposed to know this? It's not in my standard table. What can I do about cosec? This is why trigonometry is a very important topic. Because from trigonometry, I should recall that cosec is 1 over sine. That's simply for the derivative of 1 over sine x. And because they are dividing right now, we need to take this as quotient rule. Therefore, u equals my numerator, which is 1, and v is my denominator, which is sine x. Well, du dx is 0, because 1 is a constant, and dv dx is cos x. So let's apply the formula again. Do you recall the formula you should? We just used it. The y dx becomes, take your v first of all, which is sine x, bracket du dx, which is 0, minus, take your u, which is 1, times dv dx, which is cos x, all over sine x, which is my denominator, squared. Let's put the x there. So, as you are aware, sine x times 0 is 0. That's gone. 1 times cos x is cos x. All over, I will know sine x squared is the same thing as saying sine x, or sine square x. Now, some of us will be saying, okay, again, this is not in my options. So what can I do? I'm going to ask myself, can I rearrange this? Well, recall your trigonometry. What if I separate these? That will give me minus cos x dividing 1 of the sine x. And then there's nothing here, so this will be 1 over sine x. From trigonometry, what do I know? Well, simply recall that cos x over sine x is cot x. That's what we must know from trigonometry is a standard. And that 1 over sine x can be written as cosec x. Which means that my dy dx here will be minus, where I see cos over sine, that turns into cot x. And where I see 1 over sine, that turns into cosec x. When I look at my options, that is option B. So I hope we understand that this is a very easy topic, which you simply have to know the standard and apply appropriately. So I'm going to solve just 1 or 2 more questions, and we shall try to call it quits on this topic, which is differentiation. Okay, so this question comes from the year 2015, and this is question 17. Very easy question. It says y equals to x squared minus 3x plus 4. We have to find dy dx when x is 5. So straightforward, I know my expression, 3x plus 4. This is additional subtraction, so that must be the chain rule, meaning that dy dx will be, differentiate x squared, 2 comes down here, that's 2x. Differentiate 3x, the x simply goes away, that's 3. Differentiate 4, that's 0, so that's gone. And as such, dy dx when x equals to 5 would be equal to 2, x becomes 5 minus 3. 2 times 5 is 10, minus 3, and that is 7. Option D. So you see, this is very, very easy. And with that, we've come to an end of this class on differentiations. I would want to appeal to you again to please go on your own and solve as many questions as possible, including but definitely not limited to the ones I'm about to give to you. So you need to solve many questions of differentiation to truly understand and begin to remember. So I'll give you just a few to start with. And this one says the first one is from the year 2000, question 40. Then also from the year 2013, question 35. Also, take a look at the year 2001, question number 35. Also, the year 1998, question 27. That's not all. You could also take a look at the year 2006, question 11. Question 11. And last but not least, 2005, question 30. This is 3 and 0. So you can start with these and you can easily find all of these on your O3 Schools JAMB app. So please get your app and activate it. It's very, very useful for students. So I want to thank you very much for watching this video. Remember, you can comment the answers for these assignments on this video and I will definitely respond to you to let you know how you are doing. And other than that, also subscribe to the channel so as to be able to see more videos explaining various topics and various concepts. Even some videos that will give you the breakdown of the syllabus for different subjects in JAMB. All this can be gotten on your O3 Schools. So subscribe, like this video, comment whatever you want to comment, and share, of course. And we'll see you next time. My name is Athanasius.